Welcome to The Leading Edge, an MIT webinar series focused on the latest in technology, innovation, and industry, brought to you by MIT's Industrial Liaison Program. Today's event is on battery systems, featuring Zhu Li, Juner Zhu, and Martin Bazant. And now for our host, CJ Guo.
You're live.
Good morning, everybody. Welcome to the 13th Leading Edge Energy webinar. My name is CJ Guo, Program Director with the Office of Corporate Relations at MIT. As many of you know, our office has a 75-year-old industrial liaison program and a startup exchange platform through which we've been helping many of the world's most innovation-minded companies to work with MIT scientists together effectively, access MIT's leading edge research, technologies, startup communities, and the overall Kendall Square innovation ecosystem. Our extensive work in energy and climate change matters are a big part of that ecosystem. The batteries and the systems, as you know, in the recent years, have become a very important part of the solution to a sustainable low-carbon future, with the rapid growth in electric vehicles and the intermittent renewable power generation technology, especially wind and solar. And just two recent numbers. Just 2022, the world saw over 10 million electric vehicles sold. And in the same year, the power generated by wind and solar just passed 12% of the total power. And those are expected to grow going forward rapidly. Yet, challenges remaining for battery and systems in performance, cost, safety, and sustainable development. And MIT researchers are in the forefront of those research areas. So today, we've invited several experts from MIT to share their insights with us. And we want you to be part of it by submitting your questions using the Q&A button at the bottom of your screen. And we'll try to answer as many questions as we can. Now, with that, I'd like to introduce our first speaker, Professor Zhu Li. Now, Zhu is the Battelle Energy Alliance Professor of Nuclear Science and Engineering and Professor of Materials Science and Engineering. Now, he is a world-leading expert in material sciences, and he's done lots of work in the battery area. Now, today, he'll talk about materials processing and the recovery for clean energy. Professor Zhu Li, please.
Thanks, Changjin. So this is a plot of world's population. And when I was born around 1975, there was 4 billion people. But when my daughter was born near 2000, there was 6 billion. And when my son was born, there's 7 billion people. And if we look at the total
Recording
amount
in progress.
Carbon emitted from 1850 to 2019, it's this gray bar, and this was a temperature rise. The projected carbon emitted, if we follow the sort of middle of the road policies till 2050, is this orange bar. And if we don't do anything, it's going to be this deep red bar. And you can see the expected temperature rise by 2050, and then it really is going to be very bad by 2100. So there has been action in the policy space. For example, the Inflation Reduction Act, which proposes to reward EV manufacturing, for example, in this to get this tax credit, it requires 50% of the value, not the mass, to be produced in the US next year. And so there's really new opportunities for high performance materials. And just how much more materials, a number is 5 times. If you compare an electric vehicle with the traditional gasoline internal combustion engine vehicles, it requires on the order of 5 times more minerals, and for example, 3 times more copper, and a lot more cobalt, lithium, and nickel as well. And this would put a tremendous burden on the environment, in the mining, refining, in the transportation. And it's really a civilization scale endeavor if the whole world would want to replace internal combustion engines by electricity. So it's not something that we should take lightly. We should really do it correct. In my group, we have been developing high throughput experiments to understand how to make battery materials from cathode, anode, electrolyte, as well as how to recycle waste battery materials. For example, we have been developing high throughput X-ray diffraction to determine the phase of materials, high throughput self-driving electron microscopes to determine the morphology, as well as high throughput synthesis. So for example, here, we are showing synthesis of pretty complex oxides, lanthanum, calcium, titanium, nickel oxide. Traditionally, this oxide in the furnace would take up to 40 hours to get this phase pure product. But with extreme processing, such as the carbothermal shock or plasma synthesis or pulse light synthesis, we can produce these phase pure powders in just 55 seconds. And this is then coupled with the high throughput characterization to find the optimal synthesis recipes. So that was a perovskite type oxide, and this is samarium stearate. It's a fluoride type oxides. Also, we can produce pellets as well as create nanoparticles in these functional oxides by extreme electrochemical processing. So these high throughput synthesis and characterization methods are now being used in our labs in collaboration with Professor Bill Gayudis to develop high performance fuel cells and battery and electrolyzer materials. To further expand the chemical space, 4 years ago, my student Zhichu Ren have built this little demonstration where we are just mixing several salts into solvents and measuring the ionic conductivity. So the goal here is to drive so-called active learning, where you design the next set of experiments, automated experiments based on the previous experimental results. So here, after measurement, this conductivity meter is washed, dried, and then a new composition is being made, and then a new measurement is being made. So the point of this is the following. So generally, we have a very big material processing space. It could be the composition of the precursors. It could be the heat treatment process. But let's say we have done 3 experiments. Then in regions of the material design space where we have not yet done an experiment, there will be a big uncertainty. And as scientists, we would like to reduce uncertainty, because curiosity-driven research, after all, is try to make things that work uncertain into certain results. So that is so-called exploration in the materials parameter space. But as engineers, as we're running out of time in dealing with the climate issues, we would like to increase performance. And so we could be searching in the pre-existing near the prior experimental optimum, and that's called exploitation. And in active learning, the computer balances the uncertainty reduction with improvement in performance using Gaussian process regression and Bayesian optimization. So this is just showing, in this case, the computer decide actually here to do an exploration and actually hit kind of a jackpot composition and get a better performance. And last year, we have been using this approach to design catalysts. So what you see here is vanadium, copper, nickel, cobalt, chromium, manganese. So these are precursors of transition metal salts. And we first pre-mix them in a vial here to make a multi-metallic precursor solution. And then we drop cast this multi-metallic solution onto a carbon substrate. And this shows you a fast forward view of that. And unlike a traditional composition, combinatorial chemistry, each of the composition here is different. So it's not on a regular grid, but it's being proposed by the computer to be the best set of experiments to do. And then we perform this extreme processing in a few seconds, up to minutes. We can produce this high entropy alloy nanocatalyst. And then we load up these onto this carbon strips and then into this 3 electrode experiments. So here we're running oxygen evolution reaction, which is used in the water splitting electrolyzer to produce hydrogen in an alkaline solution. And what you see here is the automated linear scanning voltammetry, linear sweep voltammetry, and looks like somebody is typing, but it's really a script. And then we're able to change samples. So overnight, we can do 10, 20 such experiments. So we rinse it because it's in KOH solution. And then swap on the next experiment. So with this approach, we have developed a new catalysts for water splitting. So these are multi-metallic catalysts. However, once we put them into water, they turn into high entropy metal hydroxides, oxyhydroxides. But the upshot is we're able to, in collaboration with Professor Paul Koh at Georgia Tech, develop these high performance alkaline exchange, anion exchange membrane electrolyzers at an industrial current density of 1 ampere per centimeter squared and a pretty low voltage of 1.8 volt for now actually more than 1,000 hours. And so this is actually something we are trying to push to higher TRL level at the membrane electrode assembly and device level. So as I know the theme of today's webinar is on batteries, I would like to focus on the topic of grid scale storage, because this is what can couple to the intermittent electrical power. And what is notable about this demonstration project was it was built during COVID and it was finished in 1 year. There was a study by my colleague, Professor Jessica Transick and Professor Yiming Chang, which look at the cost to really have deeper penetration of these grid-scale storage into the electricity market. And what they found was that if the system cost reaches this level, which is not impossible, given the rapid drop of battery and system cost with lithium-ion batteries, then you can have really deep penetration into markets such as Arizona and Texas. In fact, it was predicted that at this kind of cost, out of 20 days, you can run 19 days on wind, solar, and battery storage. And there'll be 1 day out of essentially 2 weeks where there'll be a wind drought and there's not enough sun. So you have to fire up the natural gas power plants, just like in the New England area. Once you have electrical outage in the winter, you have to run the diesel generator. And so we should not demolish our fossil fuel power stations, but just use them as emergency power and achieve really deep decarbonization. So there were questions about battery cycle life. However, after recent years of study, for example, by Professor Jeff Dunn's group, this really is not the bottleneck. So by developing technologies such as pre-lithiation, where we load up lithium with some initial lithium graphite with some initial lithium inventory, or by improvement of the electrolyte formulation. For example, we have done some work with Professor Yang Shaohuan and Professor Jeremiah Johnson, where it was shown that by using this new solvent, a new family of electrolytes, we can achieve both very high voltage charging of the nickel manganese cobalt 811 cathode, as well as with lithium metal or graphite electrode. So here we show that with this new electrolyte, we can charge to extremely high voltage and get much higher energy density, but without the stress corrosion cracking and dissolution of the NCM 811 secondary particle, which is a polycrystal and tends to crack along the grain boundaries. But just by changing the electrolyte, everything else, the loading, the charging policy, the temperature, the cycle, all the same, we can effectively suppress the cracking of the cathode and prolong the cycle life of the battery. So now there is a startup company called Electrolyte Solutions, which is trying to mass market this new electrolyte systems. Is mining or manufacturing the problem? It indeed is a huge problem, because there is still a factor of 10 to 20 to go if we want to completely replace all the internal combustion engines in the world, not just developed economies. And so if we want to hit it by 2040, 2050, then we have to have year over year 25% increase in the already significant lithium mining, cobalt mining, cell manufacturing, pack manufacturing. And that is, like I said before, is not something to be considered lightly. It's a tremendous civilization scale endeavor. But in the ultimate analysis, do we have enough lithium in the world? It turns out that if you combine all the rock and all the brine resources, then there is actually just about enough lithium resource in the world to support this electrification, provided we have recycling, provided that all the used vehicles, those lithium are put back into the system to support things like stationary energy storage. But the true bottlenecks are actually technical. One is the issue of fire safety. In South Korea, there were about 500 ESS systems. But within a span of 3 years, there were 27 fires. And that's clearly not acceptable because the liability and all the insurance should be folded into the cost, and this would, just not acceptable. So very interestingly, not all the fires were caused by batteries, because there needs to be a thermal management system. There's a lot of cabling in the systems. There needs to be low voltage interfaces to the grid. So it's actually very interesting to understand what causes these fires. There's actually a lot of software issues and sensor issues that one could do to improve the system level safety, and including the practice of how to put down accidents and firemen's training. So I would like to talk a little bit about my group's research. We have done some work in developing better battery management systems by trying to use deep learning and open source data to come up with better residual life predictions, better anomaly detections, and also combining with physical models of battery aging to come up with a smart softwares. And there is a very interesting analogy to fatigue in materials, because it turns out that batteries, when you only use a low depth of discharge, it can have exponentially longer cycles to failure. So the horizontal axis here is the cycles to failure in log axis. So you see that if you only use 20% of the battery, then you really can get exponentially longer cycle life, which is analogous to the fatigue life of some kind of a steel. And there is also a very nonlinear dependence on the charging rate as well. And so you have this very nonlinear envelope of battery characteristics. On one hand, you want to do fast charging, but on the other hand, do you really need fast charging in this particular case? So knowing what the customer wants and to do the best trade-off is quite important. And in this work, we have developed a deep neural network, which takes in just one cycle of additional battery tests, and we're able to predict the residual life of the battery to within 20 cycles. So in other words, given a bunch of lithium iron phosphate batteries, some of these were heavily used before or even abused. Some of these were lightly used, but just doing one cycle of test, we're able to predict this battery has 1,200 cycles residual life, but that battery has only 300 cycles left, to an error of plus minus 20 cycles. And not only the residual life, but we're also able to predict the cycle by cycle voltage capacity curves. And this model was shown to be much better than human expert design features. For example, there were previously propositions where you can look at the change in the capacity from cycle to the next cycle, the temperature rise, or the change in impedance. So by comparing to those features, we show that the computer is actually able to resolve very subtle features, because on each charging and discharging curves, there are 500 data points that human cannot detect, but the deep neural network is able to predict. So nowadays, we're doing irregular cycle, in other words, in the real duty cycle of electric vehicles or grid-scale storage is not a full charge, 100% DOD or SOC situation. We're also combining with natural language models to build foundational models for batteries and combining with data that are coming from synchrotron in situ studies and acoustic emissions, as well as gas sensors and temperature sensors, we're trying to develop better residual life models, which can also impact safety. And finally, there is the issue of recycling. And this really is something we are obliged to solve. The reason is the track record of wind, solar, and battery in terms of reuse and recycling is pretty poor. It's actually even less than electronic waste recycling, which nowadays is less than 30%. I have known people who complain to me that even though in California, which is strongly promoting electric vehicles and renewable energies, it's extremely difficult to get license to do mining. It's extremely difficult to get license to do waste recycling. So they have to move to Arizona or very often other countries. And I think that's not a good situation. I think California should do its own waste recycling and mining, because these do have secondary pollutions. So generally, we know that pollution is a vector. It's not just carbon dioxide, it is plastics. So for example, the battery separators and packaging, we have heavy metals like nickel, chromium. We have volatile organic species like the electrolyte solvents, which are persistent organic pollutants. And so we really need to close the cycle on all these waste. If any of these is released, put to the air, or is not basically put back to the ground, like what nuclear waste is trying to do, then it's irresponsible. And we have done a study which looks at the amount of solar, wind, and lithium-ion battery waste. And in terms of tonnage, it's actually much smaller than, let's say, scrap iron recycling. But the thing is that we're just lacking technology to deal with this waste. Just to illustrate this technology gap, there was a very nice study a few years ago in this paper, which looks at the CO2 emitted for the three dominant type of cathodes: nickel, manganese, cobalt, nickel, cobalt, aluminum. So this is a Tesla battery, and this is the lithium iron phosphate battery. In three different US electrical grids, broken down into transportation, cathode manufacturing, electrolyte and anode manufacturing, and also the cell, just the cell manufacturing. Compared to the recycling approaches, where you have the pyrometallurgical recycling, which is similar to, in some sense, to the mining of the original ores. You have the hydrometallurgical recycling, where you dissolve the battery waste into acids, and then try to extract the elements like nickel or lithium element by element, or so-called direct recycling, where you try to anneal the waste powder by adding in some lithium. So it turns out that in these recycling approaches, the amount of CO2 emitted is similar to manufacturing them anew. And in fact, for lithium iron phosphate, you would actually emit more CO2 than making new lithium iron phosphate. And the process generally looks like this. So you have the waste lithium ion battery packs, and there is no industrial standard on their geometries because for the pouch cells, there is no international standards, and a lot of these are actually welded inside. So you need actually people to disassemble this by welding semi-automatically, and then it's separated into these electrodes which are connected to the current collector. So there is an issue of how to separate the active material from the current collector. And then after sorting, you can get this kind of cathode black mass or anode black mass and separator and so forth. But they are never very pure. They always have electrolyte residues. They have some of the aluminum or copper current collectors. They have plastics mixed inside. They have some other, let's say, graphite anode powder mixed inside and SEI and so forth. Professor Kamal Youssef told me, and we have done a review of the recent advances in computer vision and robotics in this step. And the conclusion is today, as of today, there is no fully automated process, although with better robotics, with better foundational models that's based on large language models, you could develop better automation. And so what we are doing now is really to improve the recycling by a light recycling and repair process to try to propel lithium-ion battery recycling to the level of lead-acid batteries, where actually 99% are recycled. Right now, lithium-ion battery is less than 20% recycled in the world. And a lot of them are just not even properly incinerated. So we have a new company called E-ion, which have developed this light recycling technology where we add lithium to the black mass, as well as some other chemicals, and we do a selective, very intense but rapid process to regenerate the lithium iron phosphate cathode. So this is the microstructure of the recycled RFP, where we actually form this very fine sub-10 nanometer grains, which is release-dated lithium iron phosphate. So this curve is the voltage capacity curve of the untreated black mass. The green curve is after our regeneration, after we put in lithium, about 20% lithium back. And the blue curve is the commercial, completely new lithium iron phosphate. So we are actually able to achieve similar capacity. And indeed, because of the recrystallized sub-10 nanometer grains, we're able to achieve at high rate even better performance and pretty good cycle life at these very high rates. And we have also developed at MIT new technologies to make single crystal NCM cathodes, which was recently published, where we can either use fresh precursors, so nickel 80%, cobalt 10%, manganese 10%, or we can use upcycled from nickel, cobalt, manganese 523. So the state-of-the-art single crystal result is in the purple. But using the upcycled waste, we're able to get still not perfect, but pretty decent gravimetric capacities. And because we are single crystal, we're able to reach a very high compressed density, electron density as well. So overall, we're able to get a volumetric energy density of the upcycled material that's close to the commercial material. And we're even moving beyond the 811, we're moving into the lithium-rich and manganese-rich single crystals, and we can produce those materials with capacity more than 250 milliampere hour per gram. That's under development. And lastly, I just want to say that there's a lot of issues with how to remove the impure elements, such as copper, which requires you to reduce it down to 100 or even 50 ppm levels. And not all the copper actually are in the zero valent form from the current collector, because you could have corrosion products that drifts from the anode to the cathode. So we have also developed methods to do that. And another very important thing at industrial scale production is product uniformity, because the incoming black mass are very varied. And so nowadays, we're applying this machine learning and active learning to rapidly tune industrial material processing, so we can achieve good product uniformity at 100 kilogram levels, depending on sort of a flexible input recycling stream. So the long-term view is that we should have a fully closed material circle, which is driven by the nuclear baseload, combined with solar, wind, and renewables, and battery energy storage, which is powered by battery energy systems, which cost less than $100 per kilowatt hour at the system level, with the initial cycle life of 20,000 cycles. But then we can do light recycling, which form a closed loop for lithium, cobalt, nickel, and also we cannot release elements like fluorine or chlorine to the ecosystem. And then eventually we can do a deep recycling, which achieves essentially unlimited cycles. So this battery is like a little mitochondria, for the global economy, and have a electricity-driven economy. And there's a lot of work to do, but I don't think there is any big showstopper, but it's just a lot of materials, chemical engineering, mechanical engineering, computer science work that needed to fully close the loop in terms of these pollutants and have a fully closed material circle. So with that, I'd like to thank you for your attention and welcome questions.
Thanks, Ju. Thanks. It's packed with lots of content, but then we got lots of questions. Some about the value chain economics emissions, some about the specific material issues. The question number one is, you said, we have actually just enough lithium on the globe if we recycle it. The question is, do we have to recycle 100% or what percentage? And then
we have to cycle close to 100%.
Close to 100%.
First of all, we're going to run out of cobalt before we run out of lithium. And secondly, if you look at the numbers, the tables, we really have to fully recycle. Yeah, it's basically a crime to discard a battery in a landfill. So we have to do 100% recovery. Yeah. Right.
And then following up to that is, you mentioned it's pretty tough to get license for the waste recycle. And the question is, the current bottleneck for recycling, is that a policy issue or is it economics?
It's actually a technology issue. We do not have technology that's scalable, and we need rapidly scalable technology. We only have 18, 20 years left. And there is also this realization that even with the best technology, there is still probably going to be some secondary pollution. So I think one has to look at the facts and just to choose to sort of the lesser poison, in the sense that we have to recognize that we're running out of time. And if we want to see it achieved by 2040, we really have to see gigawatt, even terawatt hour scale demonstrations. And you just cannot be too picky, especially in this supporting the recycling and reuse industries. Because if you look at the actual, how it is actually done, it's a heavy industry, okay? And there just has to be some recognition that, it has to be supported industry.
And you mentioned that if we can reach $150 per kilowatt hour, then you can really penetrate the stationary storage market. Then the question is, how do you compare that with the hydrogen-based storage in terms of storage time? the advantage, disadvantage of when the storage time varies?
That's a great question. So we have recently written a review in Advanced Energy Materials. Basically, the battery can only store up to 8 hours of electricity.
Right.
And so it is not a seasonal energy storage. So for seasonal, you have to use chemicals. However, hydrogen is also not a good long-term fuel because hydrogen is very easily leaked from pipes and valves. So I don't think hydrogen is good for seasonal energy storage either. But with 8 hours of storage, you can, like I said, in places like Arizona and Texas, have enough to stabilize, 20 days out of 21 days. So that's pretty good. And I have to say the $150 is system level cost. Right now, I think the actual cost is about $300 to $400 per kilowatt hour. But I still believe that that number will keep dropping. And I think it's not very far from where we can have really deep penetration into markets like Arizona and Texas.
Right. Somewhat related to that one is what test equipment is needed to test battery pack or modules for secondary like storage use, like the stationary storage for renewable power?
So that has been quite automated. So you need disassembly robots and then connect them to this potential stats, essentially battery cyclers, to do one cycle of evaluation to know, what's the residual life. So we are working on the algorithm side, but there's also a lot of hardware that is being actively developed now.
Okay. And let's do a material-related question. Are materials produced by rapid thermosynthesis process thermodynamically stable and stress-free?
Great question. So these sub 10 nanometer grains are not thermodynamically stable. The thermodynamic stability is a big single crystal, but they are sufficiently stable at room temperature. And so they actually support fast charging. So we're using the metal stability nicely because the trick here is instead of nanoparticles, which have a lot of surface area and therefore side reaction, and also the electron density below, these actually have very high electron density because we have grain boundaries instead of free surfaces. So we have both good rate capability, but also less side reaction and also good packing density. Okay.
All right. Thanks a lot, Drew. I mean, time constraint. I have to stop you there. And thanks a lot. And thanks a lot for the questions. Lots of high quality questions.